Hi everyone. So today I will be presenting my work Stable Mean Teacher for semi-supervised video action detection. This work is done in joint collaboration with Shashapan Mitra and Yogesh Singh Rawat. We are the team from CRCV lab at University of Central Florida. The problem we are solving in this paper is video action detection. Video action detection combines two things. One is action classification to recognize what action is getting performed, and the other is spatio-temporal localization to localize that action in each frame. Below are a few examples from one of the classes from UCF 101. So now the major question arrives is, can visual language models, which has been in rise since past few years, solve this problem already? It's just action recognition detection at the end. So let's see where VLMs stand. So looking into visual language models, there are two aspects, image and video. So on image aspect, they are designed for dense tasks such as object detection, image segmentation, and they also have very superior performance as against very specialized models. On the right side, we show two models which are state of the art for object detection. However, the issue with these models, they're not designed for videos. Moving on to the video-based models, they have a very strong performance again on the trivial tasks such as action recognition or action segmentation. They cannot solve dense video tasks. So for our purpose, we try to evaluate how VLMs perform for action detection. Firstly, we look into CLIP or GPT-4V, which is a multi-model GPT. However, those trivial things cannot be extended directly for this task, since they don't take video and dense situation at the same time. So to propose a solution, we look into a video model called VI Clip, which is published in ICLR 2024. The video model recognizes the action that is performed in the video, and then a detection model, Grounding Nano, which was published in ECC 2024. The Grounding Nano detects the person in the video. So now, when we evaluated the combination of Grounding Nano plus VI Clip, we saw that it fails terribly. So this proves that VLMs are still not designed or not done for the dense video task. So now, what about the specialized models? So there are three categorization of specialized models which comes into. Firstly, it's fully supervised learning. They use the video class labels as well as the frame level annotations. So this makes the task very cost intensive. The another aspect is to look into weakly supervised learning, which only uses video class labels and no frame level annotations. However, they are dependent on extra annotations which are trained, which needs from an external state-of-the-art detectors, which requires a huge chunk of dataset to be trained on. We look into another aspect, a semi-supervised approach, which is a middle ground between these, and it requires a label subset, where we have both what action is being performed and where the action is being performed, and an unlabeled subset where we have no information about the actor and the action being performed in the video. And obviously the unlabeled set is very, very huge as against label set. So semi-supervised learning incorporates of two major directions. One is pseudo-labeling, which is an offline approach and iterative approach. It involves proxy labeling. The other is consistency regularization, which is online and single step, and it includes consistent predictions. In our work, we work on the consistency-based regularization approach. So looking into existing works on semi-supervised, there has been, for dense tasks specifically, in case of images, there has been works on object detection, where the issue is it lacks temporal continuity that we cannot directly extend it to video, since we need to maintain the temporal coherence of the localization of the frames across the video. The other aspect is video action detection. So there is one work in CVPAT 2022 which propose to solve this problem. However, they look into two modules. Those two modules are disjoint and they lack correlation amongst them. And they also have the temporal constraint is also not effective at all. Now coming to our proposed approach, we start with a baseline mean teacher, which was proposed in US 2017. And we firstly adapted this for video action detection problem. So you can see that there is a student teacher approach, and then there is an EMA which transfers the weight from the student to the teacher regularly. The student is being trained and the teacher is frozen. Now, once we are done with the baseline model, we realize that it lacks precise spatio-temporal localization errors. To solve this problem, we propose an error recovery module, and following video require some kind of temporal coherency to have the localization smoothness across the frames. However, the base model lacks that still. So we propose difference of pixels to solve this problem. Now, looking into each module in depth, firstly, we look into error recovery. So the aim is to recover the fine-grained mask. And how? We firstly learn from the student mistake. As you can see, we firstly learn from the student mistake and then provide the teacher with a better supervisory signal. The characteristics of the error recovery module is that it's class agnostic, so it is independent of which class or which class of the action is being performed. And then this EO module is a small module which does not require any large pre-training at all. Now moving on to the second module, the difference of pixel, the aim is to induce the spatio-temporal coherency. So here we show two examples. One on the left is about person being static background and doing some action. And on the right, we see that a person is moving and the background is also moving. And then we see their optical flow map and realize this is the area where we should need to put extra focus to have that mask transfer very coherently across the frames. Now, how we did this approach is like we optimize the pixel difference across time. So we look into the pixel in future and pixel of the current, and then did a subtraction and then get the pixel difference map and use that as a constraint to propagate the mask across time. The characteristics of difference of pixel is that it enforces smooth flow of localization and it directly targets that pixel displacement, which is the fine-grained localization mistake that happens across for the temporal coherency. We used 4 datasets in our paper. So first is UCF101, the JHM21. To scale it for larger datasets, we used AVA. And then finally, to generalize for different dense tasks, we look into YouTube WOS. Evaluation matrix is used as against previous works. The F-map is the prediction versus the ground truth intersection versus union. And the V-map is the tubelet intersection versus the union. So we show scores for two metrics mostly, F-map at 0.5 and V-map at 0.5. So now looking at comparison with fully supervised approaches. So here you can see that we use, so our work is based on video capsule net, which uses an i3D backbone. So our work is quite robust against the fully supervised approaches, which are using 100% of the labels. And some of these papers, like they are using a huge, like TUBAR, STMixer, EVAD, and BMVIT. They require the models. They are trained on huge, large scale data. Now, moving on to the weakly supervised approach. Here also, we outperform the previous approaches by a very huge margin. And then finally coming down to semi-supervised approach, we break down into two. Firstly, we look into the image-based approaches extended for this task, such like mix match or pseudo level or like object detection aspect. And we see that the object detection based work, which is directly extended to video action detection, outperforms the previous work, which is very intuitive. However, then we look into previous video action detection works, which is CVPR 2022 and then AAAI 2024. The AAAI 2024, this one includes an active learning, an extra step, semi-supervised learning plus an active learning. Comparing against all these approaches, we see that at F-map, we outperform the previous approach by a margin of 5%. And then at V-map at 0.5, we outperform it by a margin of 6%. So this is the performance measured on UCF101. Similarly, for JHMDB, we outperform the previous model as against. Now breaking it down into ablations. So firstly, we start with the base model and then we include the EUR model, the DOP model, and finally all the modules are included. And we can see that the performance on both the datasets increases gradually, which tells that each of the module contributes orthogonals and contribute to the base model. These are the qualitative ablations, and then we can see for with both error recovery modules, there is quite a gap which these modules help to fill this thing. This helps in fine-grained localization mistakes, and then on the right side we can see that the coherency is being better maintained by using the DOP module. Now we also scale it to larger scale dataset like AVA, and we see a performance of 3.3% boost. Uh, Generalizing to YouTube, our approach also generalizes to video object segmentation, which is again a different dense video task. Now we look into other discussions. So static versus dynamic. So there are like different type of action that are performed in the video action detection, and we categorize them into two: dynamic versus static. And dynamic are more challenging, whereas our performance shows that we have a huge gain on dynamic versus static, shows that high relative boost in challenging condition. Then we look into different annotation percentage, and we see that our approach is more effective in lower level reaching. Again, we look into the error recovery architectures, and we see that 3D architecture is better than the 2D one. And then finally, we look into how the performance varies across different percentages. And then we see that our approach outperforms previous ones at all the different percentages of label data, shows that it's robust across all variation. Now moving on to quantitative analysis, we show like 4 different type of cases. Firstly, we show this boundary refinement, that you can see that even the fine-grained aspect of this is better than the 20% supervised and 100% supervised. For the noise suppression, you can see that the previous mode, like the 20% supervised, there is some noise which is suppressed by our model. Finally, this joins both the noise and the boundary refinement as against, like it's a very difficult case, and it does both. Our model is able to perform both noise suppression and the boundary refinement. And finally, the qualitative case is like about temporal mass consistency, and you can see that as against 20% and 100% supervised model, our model is a better qualitative approach. Now to summarize, we have contribution on error recovery, fine-grained error refinement, and difference of pixel for enforcing temporal consistency, and 10% annotations outperforms fully supervised. And finally, our approach scales to large scale and generalized to fine. Visit our web page for more info.